So
नमः हरि ओम् ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्युषावहै ॐ शान्ति शान्ति शान्तिः ॐ असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतं गमय ॐ शान्ति शान्ति शान्तिः ॐ सर्वेषां स्वस्तिर्भवतु सर्वेषां शान्तिर्भवतु सर्वेषां पूर्णं भवतु सर्वेषां मङ्गलं भवतु ॐ शान्ति शान्ति शान्तिः ॐ लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु ॐ शान्ति शान्ति शान्तिः ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः ॐ श्रीगुरुभ्यो नमः हरि ओम्
Good morning.
Morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am. Good morning, ma'am.
Good morning,
Good
ma'am.
morning.
Good morning, ma'am. Good morning, ma'am.
Okay. I think 184 is there. It should be more than this. Still, some of them have not joined. Okay. How was your last term courses?
Fine.
Forgot you remember. Remember. Very good. Okay. So this semester we will be studying about the vector calculus multivariable course. Okay. Is the PDF visible?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Objective of the courses, you'll be applying the parameterization of curves to find arc lengths, and you'll be familiarized with various calculus concepts applied to multivariable functions, and you'll be studying important theorems. Those are the transformation of integrals. How do we transform a single line integral to a double integral to a triple integral, and then triple integral to a line integral? So various concepts. How do we represent the integral representation for volume, area, concepts you will be studying. Okay. You will be starting with the functions, limit of the functions, that is the vector functions here, okay, and the partial derivatives, the total differential of the functions, then how to calculate the Jacobi, the Taylor series expansion. Then we go for the vector calculus, that is calculus we have studied differentiation and integration. So here you will be studying mainly vector differentiation. There are various ways in which a vector can be differentiated. That is, you can transform a scalar function to a vector function. Then the applications of those calculus concepts apply to a vector, all those things. And integration, you will be applying integration for vector functions. Three major theorems. Yes. Yeah. What is it? Someone was trying to say something. Yes, Shiva.
Ma'am, you're not audible, ma'am.
I'm not audible. Okay. So you'll be studying three major integral concepts, that is divergence theorem, Stokes theorem, and Green's theorem. Okay. So the textbook, what we'll be referring to is Advanced Engineering Mathematics textbook. I think you have already referred to this textbook for matrix algebra course, correct?
Yes, ma'am.
Yeah. So all of you have the soft copy of those textbook. For the applications of this vector differentiation and integration, the second textbook gives lot many application problems by Dennis G. Zill, author. So you can refer to this textbook also. PDF are available in net. You can download it. Okay. Anything else you would like to know? Both the classes ECE and EEE I have taught you. ECE I have taught single variable calculus. So after single variable you will have multivariable calculus. EEE students I have taught I think matrix algebra, correct?
Yes, ma'am.
Yes, ma'am.
Right. Okay. So yeah. Anything else you would like to know about the course?
Ma'am, this is a 2 credit course, right?
Yes, it's a 2 credit course. So you will be having 2 hours per week. But the syllabus is too vast for it to be a 2 credit. Earlier it was a 4 credit course along with ordinary differential. But now it has been split to 2 credit course.
Ma'am, for the evaluation, will we have the same pattern or?
If there is any pattern change, I'll let you know for the this one. Maybe next class I'll tell you about the evaluation pattern.
Okay, ma'am.
I'll just give one application like where you come across these concepts. Is a PDF file visible?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. So this is not the overall view. It's only one example what I'm giving for this particular subject. Say you have to analyze for the temperature at different regions. say you take Karnataka state, you want to analyze what are the temperatures in different areas within this state. Okay, so they can be analyzed. This is the counter plot what we see. Okay, so the counter plots explaining the regional temperatures. So they have different color variations given for the graph for the counter plots, and in this they can analyze. So they may say if it is clearly red, then the temperature will be too high in summer, and if it is slightly between yellow and green, the temperature is moderate, and if it is like blue, the variations in blue color, then it is very cold. Okay, the temperature will be around some 15, 10 to 15 or 5 to 10 degrees, like that. The variations can be given. So those things can be analyzed using your vector calculus concepts. Okay, there are a lot many things which will be given as an input for that particular concept. Okay, and then you can also go for the elevation map. Just have to look into some region map. So here I'm just showing you with the India map. Okay, so the elevation map within the regions that has been plotted with different variations for the color given. That can be shown using, so every point in the region, it can be labeled with the height of the point. So this can be another examples for all other concepts. We'll come to it with more concepts to this later. Okay. First of all, you have learned differentiation, correct?
Yes, ma'am.
Yeah. You have studied differentials of one variable. That is the ordinary differential what we'll be referring to. Okay. One second. I will not go directly with the vector fields concept. One second. Is the PDF shared? No. Okay, one second. Okay, share. Okay, is the PPT visible to you all?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so here you will have this calculus concept applied. Do you want me to increase the font size if it's too less? Yeah. Okay, so we'll go ahead. So this is also like a graphical plot of different regions what we come across. So these can be the three-dimensional surface of a surface representation of an earth with valleys, peaks, mountain ranges, and there can be many other concepts involved in order to identify certain concepts on the surfaces of the earth. Okay, and to study more about other features about those surfaces. Basically, vector in calculus deals with this type of concepts. So to start with, we'll be starting with partial derivatives. You have already studied about the differentiation of functions in calculus concepts, single variable calculus also. Okay, so there you had a function y depending upon x variable. So there you wrote the differential as dy by dx. If you have a function depending on more than one variable, that is the function depends on 2 variables, 3 variables, 4 variables, and so on. So in that case, what we do, we have to study about those functions. So I want to find the changes in the function with respect to many variables which are independent. So though there comes your partial derivative concept. Okay. So a function of several variables, multiple variables we are referring to. So here we say function depends on two variables x and y. So f is depending on x and y, And x and y can be a points representing some two-dimensional region or a plane. And if we say f is depending on the function variables x, y, z. So x, y, z are independent and f is depending on this independent variables. Then x, y, z can be representing a point in a three-dimensional space. Okay. Having. So this can be some examples for those functions. So you can have a triangular region and x, y, z representing the triangular region. You can have a hemisphere and the points x, y, z are representing the points on a hemisphere, or you can have a conical shape represented by this diagram where x, y, z are the points lying on a conical shape curve or a surface. Okay, so these can be for your vector, and you can also have these kind of surfaces representation. Okay, they are not having a particular name for it like we had in the previous case. So there we were very clear with what type of a conic they were. Here it is not clear. You have a hill kind of a structure and you are representing some curves, that is the blue lines identified. So these blue lines are like, we refer to them as functions taking constant values. What are constant functions? Can anybody define what are constant functions? What are constant functions? Kiran, what are constant functions? Venkat, Bharat? Yeah.
Ma'am, the values will be same for every input value, ma'am.
Can you give an example for a constant function?
Like f of x is equal to 4 is a constant function. Ma'am. Like that 4 is
X is
regardless.
equal to 4. Okay. Can you give a real example? This is a mathematical representation, what we say. F of x equal to 4. Can you come across some curve where you get it to be equal to constant? Graphical view, can you say? Applied to some particular field. Okay, I will give you hint for it. Say you have a temperature, a function representing the temperature. Now if I have to speak about constant function, what will be the function?
For temperature.
Yeah.
Basically, like Celsius to Fahrenheit, like that, ma'am.
Yeah, anything. Yeah, have a temperature. The function defining the temperature. In that, if I say your function is constant, what do they identify? You have studied in your chemistry or in the physics concepts.
Like
Anybody else?
9/5.
Anybody else would like to?
Ma'am, if we draw a graph between mass and temperature, it would be a constant function, ma'am.
Yeah, if temperature is constant, what do you refer to that particular region as?
Isotherms, ma'am.
Isotherms, yeah, correct. So if you have temperature to be constant in a field, in a region, then they are representing the isotherms. So if it is constant pressure, then
Isobars.
isobars, and constant volume,
Isopours.
isopores. Okay, I just gave you a hint. What do we mean by constant curves? Okay, function taking constant values. So those things you refer in different field as different concepts. So in physics or chemistry, you learn them to be, if temperature is referred as a constant, then it is a isotherm, correct? And if pressure is the constant, then they are referred as isobars, and volume is represented by some function. And if that function is taking constant values, then they are referred as isopores. So there are different names given, and if you switch on to any other field, there will be different interpretation of the functions taking constant values. Okay. Yeah. So these are kind of curves where, say, in the particular hilly region, you have the temperature to be constant, which are represented by this blue color lines. So there are various kind of pictures what we'll be bringing you. Suppose now I'll just get in the so you doing vector plots of some particular region. I'm just highlighting what all we'll be discussing. To start with, we'll be representing the isotherm curves, isobar curves. So those are the functions which are having constant values. So those are referred to as scalar functions. You know scalar quantity, vector quantities. Abhinav Shrikar. Abhinav.
Yes, ma'am. I unmuted it by mistake, ma'am. Sorry, ma'am.
It's okay. I am asking you a question. What is a vector function? Vector quantity?
Which has a magnitude and a direction specified, ma'am.
Can you give some example for vector quantities?
Means in terms of geometry or in terms of physical quantities, ma'am?
Mathematical equations.
Uh,
Or you can give it in terms of physical quantities.
in physical quantities, we have quantities such as force and velocity, etc., ma'am. Whereas in mathematics, we represent them as some xi cap plus yj cap. In that form, we represent them, ma'am.
So physical quantities, any real world examples?
Velocity, ma'am.
Only velocity, other than velocity, any other example?
Momentum, and
Hmm.
we have acceleration.
Hmm. Then
Displacement.
displacement is a vector.
Yes, ma'am.
Okay. Okay. Others? Can you quote some examples?
Torque.
Torque. Okay.
Distance.
Distance. Distance is a scalar or a vector?
Scalar, ma'am.
Scalar, ma'am.
Displacement is a vector, right? Is displacement a vector?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. So distance is not a vector. Any other examples?
Momentum.
Work,
Force.
ma'am.
I don't want the same example what is being quoted by Abhinav. Anything different you can quote.
Electric field, ma'am.
In electric field, what is a vector?
Direction of the electric field, and it also has magnitude.
Yeah, that's what. In electric field, you have electric potential and flux lines, correct? So if you say electric flux lines, they are vectors. Electric potentials are the vector?
No, ma'am.
Okay. So you don't say a field to be a vector. You have to mention in the field what is a vector quantity, correct?
Ma'am, a light is also a vector, ma'am.
Light, what?
Gravitational
In
field, current.
gravitational field or gravitational force?
Gravitational field, ma'am. Current and gravitation.
Look, when you say field, there can be, you can have both scalar and vector, correct? Asha.
Yes, ma'am.
Hmm. So you can't say it to be a field. You have now we are discussing about functions.
Ma'am, even position is a vector, ma'am.
Yeah, position is a vector. Yes.
But we can tell like electric field intensity right now.
Electric field, electric intensity.
Yes.
Electric intensity is what? Vector or a scalar?
Vector.
Okay. Any other?
Velocity.
Velocity we have already discussed.
Pressure. Normal vector to a plane.
Pressure is a scalar or a vector. Normal vector to a plane, yeah, flux lines we discussed.
Ma'am, force is a vector quantity.
Force is a vector, yes. Okay. Any other examples?
Ma'am, electric current, ma'am, it although it has magnitude and direction, it does not since it does not obey the laws of vector addition. It is a scalar quantity, ma'am.
Electric current.
Electric current, yes, ma'am.
Okay.
Ma'am, thrust, ma'am. Thrust.
Thrust, okay. Vector or scalar? Yeah. Any other examples?
Wait, ma'am.
Impedance, ma'am.
How do you calculate impedance?
Resistivity of means resistivity plus means we have formula under root of r square plus xl square minus x whole square. We have that formula.
Ma'am, it's the sum of resistance and the subtraction, like what the difference between the capacitance and the inductance square.
Those are all scalar values, right?
Yes, ma'am, it is scalar.
Ma'am, actually for calculation purpose we take mod of it, ma'am. It is a vector actually.
Actually, it is neither a vector nor a scalar, if I remember.
Impedance is vector only, ma'am.
No. Resistance, it is a scalar.
Resistance is scalar, but impedance is
Yeah.
vector, ma'am. We got the formula from the vector laws only, actually.
In the
R-
vector laws also, it is not a vector or a scalar. That is what I remember. Impedance especially. Scalar, resistance is a scalar. Look, you have your inductive and capacitive reactance to be vector quantities, correct?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Whereas resistance is a scalar.
Yes, ma'am. Resistance is scalar, but reactance is vector.
Yeah. So in that case, I don't think so. Impedance is a vector.
Impedance, reactance is vector only, no, ma'am. We get R square plus XL minus XC whole square is equal to Z square. XL minus XC is vector.
That's where I remember it's neither a vector. Depends on the field I remember. I'm not very sure. We'll check on that. As far as I remember, it's neither a vector nor a scalar, but depends on the field where you study about the impedance. Okay, so we'll start with the partial derivatives to begin with. Okay, can you see the desktop shared? Can you see the
Yes,
PDF
ma'am.
file? Yeah. So
Yes, ma'am.
now we just take some function. Let me start with function, vector function I'm just beginning with. So it is represented as v1i plus v2j and v3k. Now we have to differentiate this function with respect to x variable. So what does differentiation mean to us? It's a change in the function, the rate of change of function with respect to the variable which we are differentiating. So dou v vector by dou x if you are considering. So it's a partial change in the function v with respect to x. That is denoted by dou v by dou x. If you write dy by dx, it's a total change in the function. So y is depending on only one variable x, okay, and the function is changing with respect to x values. I'll just give an example. Say you have this function x, y, z. Now keep y and z as constant. Go on varying x values. What you get? F of x, y, z is x, y, z. Keep y is equal to 1, z equal to 1. Okay, substitute y and z value equal to 1. Now change the values of x alone. So if you are changing x values as 1, 2, 3, so on, what will be your function values?
The same values of x, ma'am.
Same values of x? Sure. Say if x equal to 1, then y and z are already fixed as 1, so you get function values to be 1. So if x equal to 2, f is?
True, ma'am. Y and z are already 1.
Okay. So now that means what? I'm changing the values of x, keeping y and z as a constant. And your function f depends on 3 variables, x, y, z. So this is the change. So you are retaining, when I partially differentiate v with respect to x, I will be treating y and z variables as a constant. Okay, so now you can find the next partial derivative, dou v vector by dou y. So when I'm differentiating v vector partially with respect to y, I will be keeping x and z variables as a constant. We'll be treating x and y, z as constants. And similarly, dou v vector by dou z, partial derivative of v vector with respect to z, if you are calculating, you are retaining x and y variables to be treated as a constants. Okay, so this is how you are going to find this partial derivatives. Okay, so can you find partial derivatives of this function? Only x, y, z, you tell me. What are the partial derivatives of the function x, y, z? What is dou v by dou x will be equal to? What will be dou v by dou x equal to?
YZ, ma'am.
Next function will be what will be the differential of the next function? Dou v by dou z.
XY, ma'am.
XY.
X, okay. Then V by dou y.
XZ.
XZ, ma'am.
XZ.
So all of you have understood what is the partial derivative. Very good. Now I'll just lightly change the function. If we are changing it to x square, y square, z square, what will be the differential of the function? So now I'm not taking a vector function, I'm taking a scalar function.
Ma'am, 2xyz, ma'am.
2xyz.
Oh, y
2x,
square,
y
z
square,
square,
z
y square,
square.
z square.
Yeah. Good. Yeah. 2x y square. Very good. Next differential will be what?
2y x square, z square, ma'am.
2y x square, y square, z square. So we are now changing the differential of f with respect to y partially. So it will be 2y x square, z square. Okay, what will be the derivative of the function with respect to z variable?
2z x
X
square,
square,
y
X square, Y square.
2z x square, y square. Okay. Now we'll change the function. C will be starting with the function as cos of x, y, z. Now don't tell the answer. All of you calculate the partial derivatives of cos of x, y, z. Once you finish, you let me know.
Ma'am, cos of xyz, when you partially derivate it with x, it is minus yz sine xyz, ma'am.
You allow everybody to understand and calculate. You finish, then we'll discuss. I told I'm giving time, correct?
Yes, ma'am.
Has everyone completed finding the partial derivatives of the function cos of x, y, z?
Yes.
Yes, ma'am.
We'll be discussing. What names those students can answer. Jyotish Vijay. Jyotish. Mohit. Jyotish, Mohit, Nakul, Krishna Murari. Pranav. Sai Chandana. Sai Chandana. Balakrishna. Balakrishna, yeah. What is the partial derivative of cos x, y, z with respect to x?
Sin xyz into yz.
Minus or plus?
Plus.
Only, not minus. Differentiation.
Ah, yes. Minus.
Is it correct?
Yes, ma'am.
Okay.
Yes, ma'am.
So you will be treating y and z as a constant. So cos ax differential will be minus a sin ax. So a constant a is y and z variables. So this will be the differential. Next person. Sai Vardhan. Sai Vardhan. Sri Bhavya.
Yes, ma'am.
Yeah, what is the next derivative? Differential of f partially with respect to y will be what?
Minus y
Minus
minus
y
xz sin xyz.
minus yes, sin. Jitendra. Jitendra.
Ma'am,
Yeah, what is the differential of f with respect to z variable partially when you differentiate?
minus of x into sin of x y z.
Any doubts with finding partial derivatives? Anyone has any doubts how to find partial derivative of a function depending on two or more variables? Okay, let's take tan inverse of y by x. I'm giving all simple functions here. Later we'll be having a combinations of functions and then we can differentiate. Next function is function depending on only two variables. Has anyone completed tan inverse of y by x differentiating partially with respect to x?
Now it's y x square by 1 plus x square.
Y can you
X square by 1 plus x square.
x square by 1 plus x square.
Yes,
1 plus x square, sure.
x plus 1, x square plus 1 or 1 plus x square. Something.
Okay, let's wait. Others.
Minus y by x square plus y square, ma'am.
Minus
X
y by
by
x square plus
x
y
square plus y square. Ma'am.
x by x square. I'm getting all different answers. Are you all doing differentiation only?
Ma'am, it's minus y by 1 plus y
Ma'am,
square.
it's minus y by x.
Minus y by 1 plus y square.
Minus y by 1
Minus
plus y
y by
square.
x square plus y square.
Minus y
Minus
by
y by
1
x
plus
square
y
plus y
square,
square.
ma'am.
It should be this answer. Only this part, minus y by x square plus y square. Tan inverse of y by x, when you differentiate, it will be 1 by 1 plus y by x the whole square into Differential of y by x with respect to x will give you minus y by x square. So if you simplify, you get minus y by x square plus y square. That is the partial derivative of f with respect to x variable. If you have got minus y by x square plus y square, it's correct. Others, can you check? You will be treating y variable as a constant. Okay? Is it fine?
Yes, ma'am.
Look, I'm not directly going for
Yes,
the
ma'am.
combination of functions. Individual functions I'm taking and I'm letting you to learn partial derivatives. Okay. Find the derivative of f with respect to y variable.
X divided by x by x
X
square
by x
plus
square plus y square, ma'am.
Yeah, x by x square plus y square. Is it clear now?
Yes,
Okay.
ma'am.
Let me change. Ln of x square plus y square. Ln, natural log. Natural logarithmic function. Ln of x square plus y square. All of you find the derivative and tell me the answer. Somebody has unmuted.
2x by x square plus y square.
Srivar, you have to give time for others to work out.
Yes.
Otherwise, they will not follow the phase in which we go.
2x by 1
Those
plus.
who understood, wait.
Okay.
2x by y x
Those
square
who
plus y
understood,
square.
wait. Those who understood, wait for a minute at least. Let others complete it.
Ma'am, could you just repeat the question?
Ln of x square plus y square.
Okay.
And you will be answering for the first partial derivative, dou f by dou x, Dhanush.
Ma'am, ln x plus y whole square, right?
Ln of x square plus y square.
Okay.
Krishna Chaitanya, Mohit Kumar, Krishna Chaitanya, Mohit. Okay, Dhanush, did you complete with the first derivative? Dou f by dou x?
No, ma'am, I'm still doing it.
Okay. Krishna Chaitanya and Mohit.
Ma'am, I got it.
What's the solution?
Ma'am, I think it's 2x plus y square divided by x square plus y square.
Ma'am, 2x by x square plus y square.
Yes, ma'am.
But you get this 2 to be cancelled off, correct? No, sorry. 2x
You,
by x square plus y square.
yes,
Yeah,
ma'am. You told
I
log
told
x.
only half is not there. Okay,
Yes, ma'am.
2x by x square plus y square. And dou f by dou y will be 2y by x square plus y square. Okay, very good. Let's go for next function. I'll give you a function, all of you do it. xyz into, are you all noting down the question?
Yes, ma'am.
Yeah, xyz into 1 plus x into 2 plus y into 3 plus z. I'll repeat, f of xyz equal to xyz into 1 plus x into 2 plus y into 3 plus z. Nivedita, you would like to answer? Nivedita? Nivedita? Nivedita?
Got it, ma'am.
What's the answer, Harsha?
2 plus y into 3 plus z into ax plus a into 1 plus x.
From where you got AX?
Ma'am, UV formula. Sorry, not a, ma'am. XYZ. I took YZ as a, ma'am. Sorry.
Okay, okay. I was wondering from where you got that constant variable A. Yeah, somebody else is trying to answer.
Ma'am, it's me, Aryan.
Yes, Arya.
Ma'am, it's 6yz plus 2xyz plus plus y square z plus yz square.
You have simplified everything, multiplied and simplified everything.
Yes, ma'am.
Okay. Okay. Any doubts with partial derivatives to anyone? Everybody has followed it?
Yes, ma'am.
Yes, ma'am.
Okay, so we'll stop with that. Next class will be continuing with the next concept along with partial derivatives. Okay, so 1 second. I'm just downloading the attendance. Once it's done, you can leave the call. One second, don't leave. Yeah, all of you can now leave the session.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.